And now we move on to the modes of heat transfer, where we have heat conduction, heat convection, and heat radiation. In the previous discussions, we simply looked at how much heat is transferred and its effect on the temperature and phase of the object. Let's now take a look at how fast heat is being transferred. And so we have heat transfer. There are three mechanisms by which heat is transferred. We have heat conduction or thermal conduction. You have heat convection and heat radiation. Let's first take a look at heat conduction. Heat is transferred through solids via the mechanism of heat or thermal conduction. Note that heat conduction also happens in fluids, that is to say in liquids and gases, but it's more dominant in solids. So, as far as our course is concerned, when we say heat conduction, we are talking about heat transfer through solids. Say you have a solid material or object, cross-section area A, and length L. On one side, you have temperature TH, and on the other side, you have temperature TC. TH, or hot temperature, and TC, what we call cold temperature. TH is greater than TC. As such, heat will flow from hot to cold, heat will flow from TH to TC. You have heat transfer rate H. Heat transfer rate tells us how fast the heat is flowing from one side of the solid object to the other side. Unit is joules per second or watts. General equation for H is Q over T, total heat transfer divided by elapsed time. For solids, heat conduction, heat rate H is equal to Ka TH minus TC over L, where K is property of the material, the thermal conductivity of the material. It tells us how well a material is able to transfer or allow heat to pass through. Unit is watts per meter Kelvin. In some cases, instead of using thermal conductivity, conduction is described in terms of thermal resistance, capital R. Unit is meter squared Kelvin per watts. The thermal resistance of the material, capital R, is given by R is equal to L over K. Be able to convert from thermal resistance to thermal conductivity and vice versa. We can affect or adjust the heat transfer rate through the material or through the object by layering different materials together, by combining different materials. And there are two ways by which we can layer materials together. We can have materials in series or materials in parallel. For materials in series, we layer the materials one after the other. You have material 1, K1, and material 2, K2, layered as shown. K1, and then after K1, we have K2. You have TH on one side and temperature TC on the other side. Temperature between the two layers, the intermediate temperature is Tx. The intermediate temperature Tx will adjust such that there's only one heat transfer rate for the object. H is equal to H1 is equal to H2. H1 is the heat transfer rate in material 1 and H2 is heat transfer rate in material 2. So H is equal to H1 is equal to H2. On the other hand, for materials in parallel, the materials are layered one on top of the other, and the heat transfer rates add up. H is equal to H1 plus H2. Next up, we have heat convection. Heat convection is the dominant heat transfer mechanism in fluids, in liquids, and gases. Thermal convection or heat convection is heat transfer via the physical motion of fluids. Because fluid is moved or moves from one location to another, heat is transferred from one location to another. Again, as I've mentioned earlier, heat conduction also happens with fluids, but it is overwhelmed by heat convection. Heat conduction is dominant in solids, whereas heat convection is dominant in fluids. Unfortunately, heat convection is a very complicated topic beyond the scope of basic physics. So I'll leave it up to you to just read your textbooks, open up your textbook to the topic of heat convection, and read the discussion. It is just discussion, no equations whatsoever to memorize. And lastly, we have heat radiation. Heat or thermal radiation is heat transfer via the emission and absorption of electromagnetic waves. Electromagnetic waves or light. In particular, we are talking about ultraviolet light, visible light, and infrared light, especially infrared light. An object both emits and absorbs, typically from its environment. An object emits and absorbs thermal radiation. H, overall heat transfer rate of the object, is still equal to total heat transferred divided by time. For heat radiation, H is equal to H absorbed minus H emit. H absorbed is the heat transfer rate that is absorbed by the object from its environment, whereas H emit is the heat transfer rate by which the object emits electromagnetic waves. H is equal to sigma E A absorb T environment to the fourth power minus sigma E A emit T object to the fourth power. Sigma is the Stefan-Boltzmann constant, and you should memorize the value 5.6704 times 10 to the negative 8 watts per meter squared Kelvin to the fourth power. Whereas E is property of the surface of both the material and the surface. E is emissivity of the surface. It does not have any units. It is a unitless quantity ranging from 0 to 1. A absorb is area of the absorbing surface. Whatever part of the object that is absorbing radiation, the area of that surface is A absorbed. On the other hand, A emit is area of the emitting surface. The environment is temperature of the environment that is surrounding the object, and T object is temperature of the object. Note that both T environment and T object should be in Kelvin. And that's it for our discussion of mechanisms of heat transfer. In the next video, we'll cover the examples for temperature and heat.